database. In this video, we are going to learn about parallel databases and distributed databases. This is one of the most critical units in modern database management system as it addresses the challenge of scale. In today's world, we deal with datasets that are so massive. Think billions of transactions, petabytes of information, that a single computer system simply cannot handle them efficiently. This unit teaches us the advanced architectural concepts and techniques required to manage these huge data volumes using the combined power of many machines. So we will be exploring two main solutions that addresses the scaling problem. The first is parallel databases, and which focuses on making a single complex task run much faster, and the second is distributed databases, which focuses on spreading the data out for better availability and managing the system across different geographical locations. We will cover their unique architectures, the performance metrics we use to measure their success, and the complex transaction protocols needed to ensure data integrity in these multi-resource environments. Okay, so let's start. Exploring the essential concepts of parallel and distributed databases is vital for handling large-scale data efficiently. Understanding their architectures, benefits, challenges, and how they improve system performance through parallelism, data distribution, and concurrent processing across multiple resources is very essential. Okay, now introduction to parallel and distributed databases. Okay, so first definition of the parallel databases. So parallel databases utilize multiple processors and disks linked by fast networks to enable simultaneous execution of tasks. This design boosts throughput and reduces response times, essential for managing large-scale data and complex queries efficiently in modern computing environments. So the core idea is simple behind parallel databases, that is divide and conquer. A parallel database is a single logical database system that utilizes multiple processors and multiple disks connected by a high-speed network, all operating in close proximity. The main objective here is sheer speed, especially for complex analytical queries. Think of it like a huge restaurant kitchen. Instead of one chef preparing 100 meals sequentially, we bring in 50 chefs to prepare 100 meals simultaneously. This dramatically increases the throughput, or the number of tasks completed per second, and reduces the response time for any single complex query. म्हणजे like parallel database system म्हणजे ज्यावेळेस एखादं कॉम्प्लेक्स टास्क असतं आणि आपल्याला ते जास्त स्पीडमध्ये किंवा क्विकली करायचं असेल, त्यावेळेस आपण पॅरलल डेटाबेस सिस्टीम प्रिफर करतो. आणि लाईक फॉर एक्झाम्पल, जर एखादं किचन असेल, तो एकच शेफ जर 100 डिशेस बनवत असेल तर त्याच्यात खूप जास्त वेळ जाईल. आणि जर आपण तेच काम जर 50 शेफ्सला दिलं 100 डिशेस बनवायचं, सो ते डिस्ट्रीब्यूट होईल आणि इझिली क्विकली लवकर म्हणजे जास्त स्पीडमध्ये करता येईल. ओके, so this is the idea behind parallel databases. Okay, now we'll move forward and definition and importance of distributed databases. So distributed databases store data across multiple independent sites interconnected by a network. They facilitate data sharing, enhance availability through replication, and maintain autonomy of sites, supporting geographically dispersed users with reliable and scalable data access. So unlike parallel systems, a distributed database stores data across multiple independent sites that are often geographically separated and connected by a standard network. The driver for distributed databases is often organizational structure and reliability. Imagine a bank with branches in London, Tokyo, and New York. Each uh, each branch needs local, fast access of its own data, but the data must logically belong to the same enterprise-wide system. Distributed databases facilitate data sharing, but their main advantage is high availability and fault tolerance. If the Tokyo sites goes down, the London and New York sites can keep running because they are independent. So basically, a distributed database is a collection of data that is stored across multiple computers, that is servers, located in different places. But it works together like a single database. Even though the data is spread out, users feel like they are accessing one single database. Uh, so so a simple example would be like imagine a company with offices in Mumbai, Delhi, and Bangalore. They store employee data. Okay, so if the system we are using for database is centralized, then there is a risk that if let's say for example we are storing all the employee data in Mumbai server and the server is crashed or fails, then nobody can access that data. Okay, and but in the distributed database system, instead we store the employee data in each city. Okay, like three, that Mumbai database is storing Mumbai employees data, then Delhi database is storing Delhi employees data, and the Bangalore database is storing Bangalore employees data. Still, all three are connected in a network. So from any office, you can view the entire company's data as if it is one database. Okay. So if one database is fails or crashes, then all the data is not lost, and all the nodes or servers are still connected, and they can access that data without having any problem. Okay. So now we will see a comparison between parallel and distributed database systems. So parallel databases focus on intra-system parallelism within tightly coupled machines for speed and efficiency. Distributed databases prioritize data partitioning and replication across loosely coupled sites, emphasizing on fault tolerance, autonomy, and data availability despite network complexities. So the primary goal of the parallel database is performance and speed up of large queries and transactions. Distributed databases primary goal is availability, reliability, and local autonomy, data loyalty, data locality. Then system coupling. The parallel databases are tightly coupled, that is, components are very close and heavily reliant on each other. Then distributed databases. Those are loosely coupled, that is, components are independent and share no physical resources. Then the data location of parallel databases. The data resides in a single centralized physical location. That is, example is one server room or data center holds all the data and all the databases. Then, but it is partitioned across storage devices. Data is geographically dispersed across multiple independent sites connected by a network. Like I gave the example of multiple cities storing employee data, like Mumbai database, Bangalore database, and Delhi database, like that. Then communication. In parallel databases, the fast high speed interconnection networks is used. That is, example is a high speed LAN. Low communication latency is obtained by using this, and in distributed databases, a slower public purpose networks are used, like internet and WAN, WAN. Mm, it generates high communication latency, which is not ideal, but distributed database provides other height, so it is cancelled out. Okay, then failure impact. uh, Parallel database has high failure risk. If the single location fails, the entire system is down. Like I explained, the parallel database are centralized system, so it has higher failure risk. Okay, then distributed databases. It they are high availability, because one of the node is failed, then that does not stop the entire system. That is, fault tolerance is very high of the distributed database systems. Then architecture typically uses shared memory, shared disk, or shared nothing architectures in parallel databases. So architecture. So distributed databases मध्ये mostly uses a shared nothing architecture, where each site has its own CPU, memory, and disk. Each site has its own CPU, memory, and disk. Then the scale. Shit. Okay, so the scale, like parallel database systems primarily are vertical scaling, adding more resources to existing nodes, and limited horizontal scaling in shared disk slash shared nothing architecture. Meanwhile, in distributed database, it has excellent horizontal scaling by simply adding new independent nodes slash sites to the network. So basically, parallel databases मध्ये nodes are physically close to each other. Nodes are connected via high-speed LAN, that is fast, reliable communication fabric. The communication cost between nodes is assumed to be small. As such, one does not need to worry about nodes crashing or packets getting dropped when designing internal protocols. Nodes can be far from in distributed databases. Nodes can be far from each other. Nodes are potentially connected via public network, which can be slow and unreliable. The communication cost and interconnection problems cannot be ignored. That is, nodes can crash and packets can get dropped. Also, network speeds are can be slow as well. So now we will see the architecture and design of parallel databases. So let's get started with it. Uh, the goal of parallel architectures is to improve performance by connecting multiple CPU and disks in parallel, and improve the availability of data, as it can be copied to multiple locations. Another aspect is to improve reliability, completeness, and accuracy of data, at the same time providing distributed access. Okay, so a parallel database is a type of database system where many processors work together at the same time to store and process data faster. The goal is to improve speed and handle large data efficiently. Now, the architecture of parallel database, uh, it completely depends on how memory is shared. Two, processors are how processors are connected, and three, the how data is stored. There are three main architectures in parallel databases. First is shared memory architecture. Then second is shared disk architecture, and third is shared nothing architecture. So the classification of parallel architectures. A parallel database architectures are defined into three groups. The most tightly coupled architecture shares the main memory. A less tightly coupled architecture shares only disks. The most frequently used architecture for databases does not share disk. The processors are interconnected and share data through message passing. Shared memory machines. Now, first type is shared memory machines, or we can say like it is the shared memory architecture. In this architecture, Each processor has access to all the memory of all processors. There is a single physical address space for the entire machine, rather than one address space for each processor. The large machines are of the NUMA type, like non-uniform memory access type, which takes more time to access data in a memory that belongs to some other processor than it does to access its own memory or local cluster. This occurs as a critical issue whether the data a processor needs should be in its own cache or not. So this is a shared memory machine where this is memory, this is okay, and this is database. Now, a shared memory architecture. In this architecture, all processors share same memory and same disk. Processors communicate through shared memory, and it is good for small systems. And it becomes slow if many processors are increased. For example, a multi-core laptop slash server is a example of this type of like shared memory architecture, and all cores access the same RAM and disk in the multi-core laptop, right? Then the shared disk architecture. In this architecture, every processor has its own memory, which is not directly accessible from other processors. However, the disks are accessible from any processors through the communication network. Disk controllers manage the potentially competing requests from different processors. The architecture is two types, depending on the units of transfer between the disks and processors. Disk farms called network attached storage, that is NAS, and store and transfer files. The alternative storage area networks is SAN, transfer disk blocks to and from the processors. Storage area networks is SAN. Okay. It transfer disk blocks to and from the processors. So basically, shared disk architecture has its own memory, but shared disk architecture. In this architecture, each processor has its own memory, but all processors share the same disk. Data is stored in a single disk system, but processors read and write through shared disk. It is good for medium to large systems, and disk becomes a bottleneck sometimes. So that is its limitation. Example is a cloud storage where multiple servers access the same database storage. Okay. Then third architecture is shared nothing architecture. In this architecture, all processors have their own memory and their own disk or disks. All communication is via the network from processor to processor. So this is a shared disk machine, and this is a shared disk machine diagram, and this one is a shared nothing machine diagram. Shared nothing machine diagram. Okay. The shared nothing architecture is the most commonly used architecture for database systems. Shared nothing machines are relatively inexpensive to build. That is why it is mostly used in the modern systems. Shared nothing architecture. In this architecture, each processor has its own memory and its own disk. No sharing. That is why it is the fastest and most scalable architecture. And processors communicate through network. So it has the best performance among all the three of the architectures stated above. Example is Google BigQuery, Amazon Redshift, or distributed clusters. So the next topic is data partitioning and distribution strategies. Data is partitioned horizontally or vertically across nodes to optimize parallel query performance. Architectures include shared memory, shared disk, and shared nothing, each offering varying trade-offs in scalability, communication, overhead, and fault tolerance. Now, parallel databases use multiple processors to store and process data at the same time. To make this possible, the data must be divided into smaller parts. This process is called data partitioning. Data partitioning is the process of splitting a large database table into multiple smaller fragments and storing each fragment on a separate processor in a parallel system. Each processor stores a subset of the data and performs tasks on it in parallel, which leads to faster query execution, uh, efficient resource utilization, and better scalability. Without partitioning, one processor handles everything, that is slow, and with partitioning, many processors handle the small parts, which is together, which gives a faster application. So, why is data partitioning needed? It improves performance. Smaller data per processor is equals to faster operations. Then also it's about is parallelism, that is multiple processors work simultaneously, that is in parallel. Uh, so the speed is definitely improved. Then scalability. It can add more processors when data grows, and the overall system becomes more scalable, that is more complex. Tasks can be divided into small parts and easily distributed into parallel system, and we can get the output or get that tasks done uh, efficiently and in very quickly. So load balancing, data distributed equally, that is no single process is overloaded, and every processor is equally optimized and efficiently used. Then reduced input output cost, smaller data chunks, that is less read and write time. Higher availability, if one node fails the others can still work. So following is the types of data partitioning. Like there are 5 common types, that is horizontal partitioning, vertical partitioning, range partitioning, hash partitioning, and round robin partitioning. Okay, so let's move forward. So types of parallelism: intra-query parallelism, intra-operation parallelism, and inter-query parallelism. Like parallelism includes intra-query, intra-operation, and inter-query, all aimed at speeding up query processing and increasing overall system throughput. Now, components of parallel database systems. Uh, Systems comprise multiple processors, memory units, disks, and high-speed interconnection networks. Architectures range from shared memory with common access, shared disk with private memories, to shared nothing where nodes operate independently, providing scalability and fault tolerance. Now, data partitioning and distribution strategies. Uh, Horizontal fragmentation assigns tuples to fragments based on predicates, enabling parallel processing on data subsets. Vertical fragmentation splits schemas into smaller parts with common keys for efficient joins, and mixed fragmentation allows deeper partitioning, supporting complex workloads. Now, types of parallelism: intra-query, intra-operation, and inter-query. Intra-query parallelism enables breaking down queries into parallel subqueries. Intra-operation parallelism distributes operations like joins, and inter-query parallelism runs multiple queries simultaneously. This parallel execution reduces response time and optimizes resource utilization. Now, so now we will see the distributed database environments. Distributed database is grouped into homogeneous and heterogeneous distributed database environments, each with further subdivisions as shown in figure. So, a distributed database system is divided into two parts. That is, first is homogeneous, which is further divided into autonomous and non-autonomous distributed databases. Uh, then distributed database systems divided into heterogeneous, which is further divided into federated and unfederated distributed database systems. Now, a homogeneous distributed database is a in this database, every one of the sites uses identical database management systems and operating systems. Each site is aware of all the other sites and cooperates to process user requests. The database is accessed through a single interface as if it is a single database. It can be of two types. If the database is independent and functions on its own, it is called autonomous, and it is integrated by a controlling application and uses some message passing. In a non-autonomous database, data is distributed over many nodes and a master of DBMS coordinates data updates. Now, heterogeneous distributed database. In this type of database, all the sites use different schemes, operating systems, and data models. It can be composed of various DBMS, that is relational, network, hierarchical, object-oriented. Hence, query processing is complex due to dissimilar schemes. Furthermore, transaction processing is also complex due to dissimilar software. A site may not be aware of others, thus there are limited help processing user requests. They are of two types. Federated is independent in nature and integrated together. They function as a single database system. Unfederated employs a central coordinating module through which the databases are accessed. Now, distributed database architecture. Now let's see the architecture of distributed databases. Now the main components of distributed database architecture are database that is stored at multiple sites, then computer nodes that are sites, and 3 communication network, and 4 distributed database management system, that is DDBMS. Now in the workflow of this is users send query to the DDBMS processes, which fetches data from required sites and returns the result. Now, types of distributed database architecture. There are 3 main architectures. First is client-server architecture. Second is peer-to-peer or fully distributed architecture. And 3 is multi-database federated architecture. Let's see them in detail. Like first is client-server architecture. In this model, data is stored in one or more server machines. Users access data by sending requests. There is a clear separation. Clients make requests, and server processes and returns results. Now, for example, you use a mobile banking app. That is, you are a client and you request balance info. The server holds the database and that server sends the balance to you. That is simple and easy to manage. If server fails, then we have no access. Distributed database management system architectures are developed on 3 parameters: distribution, autonomy, and heterogeneity. Distribution states the physical distribution of data across different sites. Autonomy indicates the distribution of control and degree to which each constituent DBMS can operate independently. Heterogeneity refers to the uniformity or dissimilarity of the data models and system components. Some of the common architectural models are client-server architecture. It is a two-tier architecture where the server primarily encompasses data management, query processing, optimization, transaction management, etc. The client mainly provides a user interface. Peer-to-peer architecture. Each peer acts both as a client and a server. The peers share their resources with other peers and coordinate their activities. Multi-DBMS architecture. So where were we? So peer-to-peer architecture. Each peer acts as both as a client and a server. The peers share their resources with other peers and coordinate their activities. Multi-DBMS architecture. It is an integrated database system formed by a collection of two or more autonomous database systems. Distributed query processing. Distributed query processing is the procedure of answering queries in a distributed environment where data is managed at multiple nodes. Query processing involves the transformation of a high-level query into a query execution plan, which consists of lower-level query operators in some variation of relational algebra and its execution. The goal is to produce a plan which is equivalent to the original query, returning the same result but more efficient. Now, distributed commit. Distributed commit is a complex protocol to determine whether to commit a distributed transaction uniformly. A transaction manager conveys the decision to all nodes where the transaction is being executed. When transaction is complete at a site, it reaches a particularly committed state, partially committed state, and waits for other sites to reach same. After receiving a message that all sites are ready, it starts to commit. Different distributed commit protocols are one-phase commit, two-phase commit, and three-phase commit. That means if म्हणजे जर ऑल सगळ्याच नोड्सनी जर परमिशन नाही दिली कमिट करायची तर तर ती जी ट्रान्झॅक्शन आहे ती पार्शियली कमिट स्टेजमध्ये राहते आणि ज्यावेळेस ऑल द नोड्स परमिशन देतात की त्यावेळेसच ती ट्रान्झॅक्शन फुल्ली कमिट होते आणि सर्व डेटाबेसेसमध्ये reflect करते. Then related work. Non-uniform memory architecture, that is NUMA, and clusters like SAN and NAS are few examples of parallel database systems. There are many distributed database implementations such as Cassandra, Apache HBase, MongoDB, Neo4j, and CouchDB, TerraStore, FlogDB, Redis, React, OrientDB, etc. Thank you. So now we are going to see the client server versus peer-to-peer architecture models. Client server systems have centralized control with clients requesting service from servers, simplifying management and ensuring consistency. Peer-to-peer structures decentralize control among equal nodes. enhancing scalability and fault tolerance but increasing coordination overhead. Distributed database components and middlewares. Local database managers control site-specific data, with transaction coordinators overseeing global execution. Middleware abstracts heterogeneity and manages query processing, concurrency recovery, and ensures a unified database interface despite distributed infrastructure. Data distribution strategies, that are fragmentation, replication, and allocation. Uh, Effective fragmentation and replication balance system performance, availability, and update costs. Proper allocation places data near users to minimize latency, balancing storage overhead against improved query responsiveness and fault tolerance. Client-server versus peer-to-peer architecture models. While client-server architectures ease integrity enforcement and administration via dedicated servers, peer-to-peer models distribute data control, improving resilience and scalability. It requires complex synchronization mechanisms for consistency. Distributed database components and middleware. Middleware plays a critical role in managing distributed queries, concurrency control, and failure recovery. It harmonizes differing local systems to provide a coherent and transparent global database experience to end users. Now, now we will see the query processing and optimization, query decomposition and parallel execution. Decomposing queries into parallel subqueries allows simultaneous processing across distributed nodes utilizing data locality and parallel computing power to reduce execution time and improve throughput. Distributed query optimization techniques. Optimization minimizes communication costs by selecting efficient join orders, pushing operations close to data, and balancing resource use. Cost models incorporate network delays and node workloads to produce optimal execution strategies. Handling communication overhead and load balancing. Load balancing nearly evenly distributes query tasks to prevent bottlenecks. Communication protocols reduce latency and bandwidth usage, essentially for maintaining responsiveness and scalability in distributed environments. Query decomposition and parallel execution. By distributing subqueries among processors or sites, systems act, uh, sy- systems achieve concurrency in data retrieval and processing. This approach significantly lowers query response times, capitalizing on the parallel infrastructure. Distributed query optimization techniques. Advanced optimize Advanced optimizers analyze data placement and network topology to recognize queries for minimum data transfer and efficient execution, ensuring optimized resource utilization and faster responses. Handling communication overhead and load balancing. Minimizing internode data transfer and balancing workload are for are critical for performance. Techniques Techniques focus on reducing communication delays, avoiding hotspots, and maintaining system availability during peak demands. Query decomposition and parallel execution. Parallel execution of decomposed queries empowers databases to handle complex large-scale workloads efficiently by taking advantage of multiple processing units working in tandem to speed operations. Distributed query optimization techniques. Distributed optimizers employ cost-based models considering communication and computation costs. Strategies include selective data retrieval, operation pushdown, and parallel join execution to enhance overall performance. Handling communication overhead and load balancing. Effective coordination in distributing work and communication helps avoid resource contention and network congestion. Sustaining high throughput and consistent query processing across distributed architectures. Uh, so now let's see the most important questions for exam point of view. Uh, so the first question which you should be prepared for the exam is, what are advantages of parallel database? Explain shared memory, shared disk, and shared nothing parallel database architectures. So the advantages of parallel databases are as following. Parallel databases are used to multiple processors. Parallel databases use multiple processors to work together. This makes database operations faster and more efficient. First, high performance and fast processing. Many tasks run at the same time, therefore queries finish faster. Better scalability. More machines can be added when data increases. Performance improves as you add processors. 3. High throughput. Can handle many users and queries at the same time. 4. Fault tolerance. If one fails, if one processor fails, others continue working, depending on the architecture you be using. Cost effective. Uses low cost hardware connected together to get high performance. Parallel database. Parallel database architectures. Parallel databases are categorized based on how processors share memory or storage. There are three main architectures: shared memory, shared disk, and shared nothing. In the first, shared memory architecture, it means all processors share one common main memory. All processors also share same disk storage. Features of shared memory architecture. It is simple to design, fast communication because of memory is shared, and the advantages of this architecture are easy to program, fast data access, and good performance for small systems. Meanwhile, the disadvantages of this architecture is limited scalability. That is, cannot add too many CPUs. More CPUs equals to more memory conflict. Small multiprocessor systems use this architecture. Second is shared disk architecture, meaning each processor has its own memory. All processors share the disk. Features are: data is accessible to all since disk is shared. Then advantages: better fault tolerance. If a CPU fails, data is still safe and more scalable than shared memory. Disadvantages: disk access becomes a bottleneck. Everyone depends on same disk. That's why sometimes disk access becomes a bottleneck. Requires synchronization to avoid conflicts. It is used in clustered systems. Then shared nothing architecture. Its meaning is each processor has its own memory and own disk. No sharing of memory or disk. Complete independence. Advantages are highly scalable, that is, it can keep adding machines. No contention, that is because there is no sharing, and very good performance is obtained by this architecture. It is most common used architecture, which is share nothing architecture. But the disadvantages of this architecture are: it is more complex to manage and data must be moved between nodes when needed. Therefore, it has some communication cost attached to it. Okay. Now, it is used in large distributed systems like Google, Amazon, etc. Now, simple real world examples like shared memory is architecture can be understood like a small server with multiple CPUs. Then shared disk, a database cluster sharing SAN storage. And a shared nothing architecture is like Hadoop cluster or Google Bigtable. So let's move forward with the second question. So that question is: explain parallel query optimization in parallel databases and explain performance parameters of our parallel databases. So let's start this answer. Parallel query optimization refers to techniques used by a parallel database system to efficiently divide and execute a query over multiple processors/nodes simultaneously. The goal is to reduce query response time and improve throughput. When we submit a query, instead of executing it on a single CPU, the system breaks the work into smaller tasks and executes them in parallel. Now, key steps in parallel query optimization. Query decomposition. The given SQL query is analyzed and broken into relational operations like select, project, join, group by, etc. These logical operations are converted into an internal representation for optimization. Example: select name from employee where salary is greater than 50,000. Now selection plus projection. Choosing parallel execution strategy. Parallel DBMS analyzes execution plans and chooses how to run tasks in parallel. Intra-operator parallelism. A single query operator like join is parallelized. Example: each processor joins part of the data. The benefit is significant speed up. B. Inter-operator parallelism. Multiple operators run at the same time. Example: while selection is being done, projection also processes outputs in a pipeline. Now, pipeline parallelism. One operator's output becomes the input for the next without waiting for completion. Enables streaming of data between operations. Parallel optimization techniques. Data partitioning. To parallelize a query, data is first partitioned across nodes. Common strategies are hash partitioning, range partitioning, round-robin partitioning. The benefits are balanced distribution, reduction of data movement. Parallel join techniques. Joins are expensive operations. Optimizations include hash join. Both relations are hash partitioned on join key. Each processor joins its subset. Sort merge join. Relations are sorted then merged in parallel. And see broadcast join. Smaller relation is broadcast to all processors. The third part of the answer is minimizing data transfer. Communications cost is reduced. Data movement between processors is expensive, so optimizer tries to push selection to data node and reduce intermediate result size, avoid unnecessary repartitioning. Then predicate pushdown. Conditions are pushed closer to data location, helps reduce size of data early. Load balancing. Work must be distributed evenly across processors. If some processors are overloaded while others are idle, the performance drops. Scheduling optimization. System decides which task runs where, task order, resource allocation. Goal is to reduce idle time and maximize parallelism. Query rewriting. Query may be internally rewritten for efficient execution. Converting nested subqueries into joins for better parallel execution. And using indexes in parallel. Data partitions may have separate local indexes. Lookup happens in parallel, improving speed. Benefits of parallel query optimization. It gives faster query execution, high throughput, efficient resource utilization, and ability to handle large data sets. Now, performance parameters for parallel databases. Performance of parallel databases is measured using several parameters that help evaluate how efficiently the system performs when adding more processors. First is speed up. Speed up measures how much faster a task runs on multiple processors compared to a single processor. Speed up is equal to time on single processor divided by time on n processors. Ideal speedup is linear, that is 4 processors should be working as 4x faster, and real speedup is usually less due to overheads. Then example is single processor time. If it takes 100 seconds, then 5 processors time is 24 seconds. That is speedup is happened 4x times instead of 5x, which is ideal speedup. Second is scale up. Scale up measures systems' ability to maintain performance when both data size and resources are increased proportionally. For example, one CPU handles 1 GB in 10 seconds, then 10 CPUs should handle 10 GB in 10 seconds. Shows how system scales with data growth. Third is size up. Size up measures how performance changes when only data size increases. Example is if double the data takes slightly more than double the time, then good size up. Throughput. Number of tasks completed per unit time. Higher throughput should explain the better performance. used when multiple users query multiple users/query workloads exist. Response time. Time taken to complete a single query. Goal is to be minimize the response time even with large data sets. That is, uh, time taken for a single query should be minimized. Okay. Then efficiency. Efficiency measures how well processors are utilized. Efficiency equals to speed up upon number of processors. If speed up is equal to 8 using 10 processors, if then efficiency is equals to 0.8, that is 80%. Higher efficiency is good utilization of resources. 8 is fault tolerance. Ability to continue operations even when some nodes fail is important in distributed parallel environments. Okay, that is it. So let's take the next question. Explain data replication and data fragmentation in distributed data storage. Okay, so first is fragmentation, occurs sharding, splitting one logical data set, splitting one logical data set or table into pieces, that is fragments or shards, and storing each piece on different nodes or regions to parallelize work and keep data close to where it is used. Replication. Keeping copies of the same fragment on multiple nodes to improve availability, fault tolerance, and read performance. You almost always use both. First fragment to scale out and then replicate each fragment for high availability. Data fragmentation, that is sharding. Why fragment? Scale out writes and storage. Spread hot tables across machines. Then performance and locality. Queries hit smaller pieces, keep user and region data close to its users. Then isolation of failures. One shard's issue doesn't take down all data. Correctness goals. That is very important. Reconstruction. You can rebuild the original relation from fragments. Completeness. 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 No tuples are lost. All original tuples appear in some fragment. Disjointness. Same tuple does not appear in more than one fragment unless it is replicated. Lossless join. Joining vertical fragments on the key recovers the original table. Common fragmentation types. Horizontal fragmentation. Split by rows using predicates. Arrange list natural when you have geography, time, periods, and tiers. Hash key. Balances load evenly, avoids hotspots, directory based. Maintain a lookup mapping key, that is shard, flexible extra hop. Pros are easy routing and great for PyKey queries. Cons are cross shard joins and aggregations cost more risk of skew. Vertical fragmentation. Split by columns around access patterns. Keep frequently accessed columns together and push bulky rare columns aside. Ensure primary key, that is ID, is present in every vertical fragment to enable lossless join. Pros are reduces input-output, memory, and good for columnar stores. Cons are extra joins when you need wide rows. Hybrid fragmentation. Combine horizontal plus vertical for fine control. Example is first split then by region and then split each region's table into fact versus wide attributes. That is vertical. Designing fragments practical steps. First is workload analysis. Top queries, filter, joins, hotkeys, etc. Choose charts, chart keys. Aim for even distribution and locality. Then co-partition related tables. That is chart and by the same customer order key to make joins local. Plan for growth. Use consistent hashing or pre-split ranges to ease rebalancing. Skew handling. Add a solve to hotkeys or subshard popular tenants. 3 is data replication. Why replicate? High availability. Node or AZ failure is not equals to data loss. Disaster recovery. Copy in a distant region. Now sync modes and consistency. Synchronization and replication. Ledger waits for followers before ACK. Asynchronous replication. Leader ACKs immediately followers catch up. So let's see the final question, that is question 4. What is concurrency control in distributed databases? What are the potential problems of concurrency control in distributed databases? And what is need of concurrency control methods in DBMS? Okay, so the concurrency control in a distributed databases management system is the set of mechanisms used to coordinate the simultaneous access of multiple transactions to share data that is geographically spread across multiple independent sites. Its primary goal is to ensure that the execution of concurrent transactions is serializable, meaning the final state of the database is equivalent to some serial non-interleaved execution of those transactions, thereby preserving data consistency and integrity. Why concurrency control is needed in DDBMS? The necessity of concurrency control in a DDBMS is to safeguard the ACID properties, that is atomicity, consistency, isolation and durability in a multi-user, multi-site environment. The need is maintain data consistency because it ensures that concurrent operations do not violate database integrity constraints or leave the database in an inconsistent state across sites. To ensure transaction isolation, it guarantees that the changes made by one transaction are not visible to the other transactions until the first transaction is successfully committed. Then to prevent anomalies, it is crucial to prevent classical concurrency anomalies that are amplified in a distributed setting. Lost updates, dirty reads, that is reading uncommitted data, and unrepeatable reads. Then manage data replication. If data is replicated, that is stored at multiple sites, concurrency control is essential to ensure that all copies are updated correctly and remain consistent with each other. Now, potential problems of concurrency control in distributed database management system. Concurrency control is significantly more complex in a distributed environment than in a centralized one due to the inherent characteristics of distributed systems, that is lack of global clock, communication latency, and site failures. Now, distributed deadlock. A deadlock occurs when a set of transactions is waiting for locks held by other transactions in the set. Forming a cycle detecting a deadlock is harder because the weight for graph is spread across multiple independent sites, requiring complex time-consuming global deadlock detection algorithms. Coordinating transactions across sites requires frequent network communication to request and grant locks or share timestamps. This communication introduces significant network latency and overhead, potentially reducing the benefits of concurrent execution. When a data item is replicated across multiple sites, a write operation must be propagated to all copies. The concurrency control mechanism must ensure that all copies are updated atomically using protocols like two-phase commit and in a globally consistent order. Ensuring serializability across all local transactions schedules at different sites is challenging. The local concurrency control mechanisms must cooperate to enforce a single global serialization order for all distributed transactions. A transaction might commit at one site but fail at another site. Due to the site crash, robust mechanisms are needed to coordinate commit decisions or abort decisions across all sites to maintain atomicity. Example is using the two-phase commit protocol. Thank you. In conclusion, parallel and distributed databases are the engines that power the modern data world. Parallel systems give us the raw power to execute complex queries fast, primarily through the shared nothing architecture. Distributed systems give us the necessary resilience and availability by coordinating data through fragmentation and replication. However, both introduce immense complexity, particularly around transaction management, where protocols like two-phase commit are essential through imperfect for ensuring consistency. Now, now, thank you for walking with through this detailed overview of Unit 5 with me, and I'd like to thank you all for your attention and watching this video. And इतना बोल के मैं अब ये वीडियो ख़त्म करना चाहूँगा. थैंक यू ऑल.